Swayam Prabha. Digital India. Educated India.
Good morning. Today is the second lecture in the series of lectures on structural analysis. In the previous lecture, we discussed how to calculate the static indeterminacy of a structure. Today, we are going to be discussing how to compute the kinematic indeterminacy of the structure. Kinematic indeterminacy. What do we mean by the kinematic? The static indeterminacy you saw last time was essentially how to compute the number of redundant forces that you have in the system, which if you removed would make the structure statically determinate, and you could then solve and find out all the forces in the structure purely by using equations of equilibrium. Now, kinematic indeterminacy, this is a completely different concept altogether, although in other words, the word kinematic indeterminacy is actually a misnomer. It is more commonly known as the degrees of freedom that a structure has. What is this? Degrees of freedom. What exactly is this? If you were to describe it in words, it is the minimum number of displacement quantities that you require to know before you can define the displaced geometry of the structure. Okay. Now, so therefore, if you look at this is completely different. Although we are using the same word indeterminacy, it's a completely different concept. The previous one referred to how to find out the forces in the structure. This one is referring to how to find out the displaced geometry of the structure when it is subjected to loads. And note, the kinematic indeterminacy is the minimum number of independent displacement quantities that you need to define to be able to get the complete displaced geometry of the structure. Let's look at a structure. And what I will do again, just as I did in the last lecture, where I looked at two different types of structures. One set of structures which are made up of only axially loaded members. If you remember, those are trusses. So I'm going to start off with trusses because even trusses and beams and frames, which are essentially structures made up of members which can deform flexurally, are different. The treatment is different. Let us look at a truss. And again, I go back to the simple truss that I had last time. Simple truss. Now, we want to find out what the kinematic indeterminacy of this truss structure is. Before that, I need to define what a kinematically determinate, remember, it's very easy for you to know how to get the statically determinate structure. You know when you look at it what a statically determinate structure looks like. How do you see a kinematically indeterminate structure? Let's take this same structure and I want to make this kinematically indeterminate. How will I make it kinematically indeterminate? This is a kinematically determinate structure. Why is this kinematically determinate? Let's look at this structure. See, understand what is kinematic indeterminacy. It's the minimum number of displacement quantities that you need to define the displaced shape of a structure. Let's look at this structure. How will it displace? Under loads, how will it deform? Let's look at this. Can this point go anywhere? This point cannot go anywhere because it's restrained both in this direction as well as this direction. It cannot move anywhere on the plane. That means this point cannot go anywhere. Can this point go anywhere? Neither can this point go anywhere. Can this point go anywhere? Again, it can't. Simply because every point has a hinge which restrains the displacements in the plane of the structure. Okay. So, what would be the displaced shape of the structure if it were subjected to loads? Think about it. Let's put some loads on the structure. These are the possible loads on a truss structure, because remember, a truss structure can only be loaded at the joints. So I put all possible loads that this structure can be subjected to. What would be the displaced shape under these loads? Remember, nothing. Under these loads, all these loads would get directly transferred to the supports, and the structure will not be subjected to any stress. So therefore there is going to be zero strain, and since there is going to be zero strain, there is going to be no displacement. So what's a kinematically determinate structure? A structure that does not displace. Simple. Okay. Is that interesting? Well, currently it's not interesting. Later on we will see that we need to define a kinematically determinate structure before we can use what is known as the displacement method of analyzing statically indeterminate structures. Okay. Once we have a kinematically determinate structure, now it's very easy to look at this structure and see how this structure, or what is going to be the kinematic indeterminacy or the degrees of freedom of this structure. Let's look at it. This point, can it go anywhere? No. Again, there's a hinge which is restraining it from moving anywhere. Can this point go anywhere? What's the restraint? The only restraint is it cannot move vertically. Okay? It cannot move vertically. So therefore, but is there any restraint for moving it horizontally? No. So this is a possible displacement. This node can displace in this direction, and therefore this horizontal displacement is a degree of freedom of the structure. Let's look at this point now. Can this point go anywhere? Note that this point can go anywhere on this plane. And in a plane, how many displacements do you require to define? Well, if you know, if you define two orthogonal displacement quantities, they completely define the displacement of this point anywhere in space. So now, if you look at it, this structure, simple truss, has three nodes. One node completely restrained, cannot go anywhere. This node vertically restrained, can move horizontally. This node free to displace in any way, direction it wishes in the plane. So it has, we can define two displacement quantities which will define the motion of this point anywhere in space. Okay. So now, how many degrees of freedom, or what is the kinematic indeterminacy of this structure? 1, 2, 3. So the kinematic indeterminacy of this structure is equal to 3. Simple? Yes, very simple. So therefore, if you have a truss, any joint in the truss can move in the plane. And what you need to look at is what are the restraints. So now I can look at it this way. Let me redefine this problem. How many nodes? So I'm not going to do an algorithmic way of getting the kinematic indeterminacy. How many nodes? This structure has 3 nodes. Right? Okay. So now for the movement of a node or a joint, you can call this a joint too. Joint, node, same. So the movement of a joint in a plane is given by 2 independent displacement quantities. In other words, if I know those 2 displacement quantities, I know where the joint is in the space. So therefore, let's look at it this way. How many joints? 3. How many degrees of freedom per joint? Degrees of freedom are 2 per joint. So therefore, if this plane truss were to have no supports, what would be the degrees of freedom? It would be 2 into the number of joints, so it would be 6. So the degrees of freedom, 2 per joint multiplied by 3 is equal to 6. 6 degrees of freedom, since this truss has 3 joints. Now this is the unrestrained degrees of freedom. In other words, the truss did not have any support. Then the number of degrees of freedom would be 6. However, you do have 2 supports in this structure. What are the supports? At one joint you have a hinge. A hinge, what does it stop? It restrains. So restraints. Restraints. At this node, a hinge will have 2 restraints. What are the 2 restraints? It stops it from moving vertically. It also stops it from moving horizontally. So it does not allow this joint to go anywhere. So it gives 2 restraints to this joint. Okay, what about this joint? This kind of roller joint. How many restraints does it give? It gives exactly 1. It restrains the vertical motion of this joint. Okay, it gives 1. And 1 meaning 2 plus 1. So the total number of restraints in this is 3. So what is the restraint structure? How many degrees of freedom does it have? 3. Simple. Same kinematic indeterminacy by finding out the displacements, and also the algorithmic way. Find out the number of joints in a truss, multiply that by 2, that gives you the unrestrained degrees of freedom. You find out the number of restraints that the body has, and then subtract those restraints, and you have the degrees of freedom or the kinematic indeterminacy of the truss. Okay, let us look at one another problem. Let us look at a slightly more complicated truss. Let me just draw another one. This is the truss. Okay? And if you look at this truss, we have to find out the kinematic indeterminacy. How would I go about it? Now we're going to use only the algorithmic way of getting it. And then I will show you which are those displacements. How many joints? 1, 2, 1, 2, 3, 4. Joints. 4. So, what are the number of degrees of freedom? Note that kinematic indeterminacy and degrees of freedom are used interchangeably. Okay? So, what are the degrees of freedom per joint? For a planar truss, 2 degrees of freedom. So, what is the total number of unrestrained degrees of freedom? Unrestrained degrees of freedom is equal to 2 into 4, 8. Okay. So, that is the unrestrained degrees of freedom. Now, we need to find out what the restraints are. Restraints, here 1 hinge support, 2 restraints, 1 roller support, 1 restraint, so 3. So, what is the total actual degrees of freedom? 8 minus 3, that is 5. So, the kinematic indeterminacy is 5 for this structure. Now, once I have defined the kinematic degrees of freedom, okay, you need to now see, well, that's a kinematic indeterminacy 5. Now, you always understand what kinematic, remember what kinematic indeterminacy is. What is it? The minimum number of displacement quantities that you need to define to be able to get the displaced geometry of the structure. So, now I need to find out and define those displacement degrees of freedom, and note that I should have only 5 independent displacement degrees of freedom. Let us find out. Let us look at this node. Any degrees of freedom at this node? No. Both of them are restrained. Let us go to joint 2. Restrained? None. What are the degrees of freedom? 1, 2. Let us go to 3. Any restraint? No. What are the degrees of freedom? 1, 2. The vertical displacement and the horizontal displacement. What about 4? Well, it's restrained in this direction. It's not restrained in this direction. So, now how many do I have? I have 1, 2, 3, 4 and 5. 5 degrees of freedom. 5 kinematic indeterminacy. So, therefore, it should be fairly easy for you now to get the kinematic indeterminacy of a truss type structure. Planar truss, 2 degrees of freedom. Space truss, 3 degrees of freedom, because you need 3 displacement quantities to define the position of a point in space. 3 independent, x displacement, y displacement and z displacement. Now, what with the unrestrained degrees of freedom for a space truss? 3 into the number of joints, that will be the unrestrained, and then you find out the number of restraints that you have, which are, what are the restraints? The support conditions, the supports, the restraints provided by the supports. Subtract the restraints, you've got the degrees of freedom for a truss, and that defines your kinematic indeterminacy, or for a truss structure. Now, let's move on to that for a frame. Well, let me start off, before I go for a frame, let me start off with a simple one, which is a beam. Let's look at a beam. So, let me look at a very, very simple beam. This is a structure that you are all familiar with. What is this? A simply supported beam. Okay. What is the static indeterminacy of the simply supported beam? 0. You know that. It's a statically determinate structure. But now we are not looking at static indeterminacy. We are looking at kinematic indeterminacy. Now note, you will say, well, again, there are 2 joints, 2 nodes in the structure, right? And you can say, well, Why don't we use the same thing as the truss? Every node, for it to move in the space, for it to move it in the plane, there will be 2 degrees of freedom. Okay? And 2 nodes, 2 degrees of freedom. Let me define that there are how many? 3 restraints. So this is kinematical. So if you use the truss model, 2 into 2, 2 nodes, 2 degrees of freedom per node, that's 4. And there are 3 restraints, 2 here and 1 here, and 1 degree of freedom. What is that 1 degree of freedom? This one. Is that correct? Is this a single kinematically indeterminate structure, a single degree of freedom? No. Because you have to understand that members in a beam and frame behave differently from a truss. A truss is only an actually loaded member. So all we need to know is where the 2 joints at the end of a truss member is, and that gives us the elongation of the truss, and from that we can find out the force in the truss. Simple? Yes. Can we do that for a beam? No. Why? Because you have to understand that the whole concept of a beam, the behavior of a beam, the way it's loaded, how is the beam loaded? It's loaded in this manner. What happens to the beam? The beam goes like this. You see? So therefore, the entire concept of displacement, degrees of freedom for a beam and a frame would be different from that from a truss, and that is why we need to look at it differently. Okay. So now, how do we look at it differently? And that's where an important point comes in. A joint that connects beam members or frame members, in addition to the 2 degrees of freedom which define its movement, also has another additional degree of freedom. What does that do? That degree of freedom actually defines the movement of the members relative to each other. And what is that? And that degree of freedom is the rotation degree of freedom. Okay. So, therefore, whenever you look at a beam or a frame, every joint, when it's unrestrained, has 3 degrees of freedom. So a joint has 3 degrees of freedom. What does this degree of freedom do? Look at it. Think of this. Let me fix this. If I fix this and this disappears because this cannot go up or down. Does that mean that, remember, that if I have a kinematically determinate structure, I can define the displaced geometry of the structure completely. Can I? Think about it. If I restrain this and I restrain this, okay, both the displacements are restrained. Both the displacements are restrained means what? No displacement. But is that true? No. Under this load, it displaces in this manner. So therefore, understand that I require additional displacement quantities to define the displaced shape of the structure. And what are those? Look at this. This rotation and this rotation. These 2 rotations gives me the displaced shape of the structure. Okay? So therefore, that is that additional degree of freedom that I need to define. So therefore, whenever you have a beam or a frame, you have 3 degrees of freedom per joint. Now let's come back to this structure that I had. The simply supported beam. How many degrees of freedom does it have? Now let's look at it. How many joints? 2. How many degrees of freedom? For the unrestrained degrees of freedom? 3 per joint. So total 6. Right? Accept that? 6. Okay. Number of restraints? Note that this hinge support still restrains only two, which is that this displacement and this displacement. Okay, so it has two restraints. And how many this? 1. So what is the total number of restraints? 3. So what is the degrees of freedom? 3. So in other words, this simply supported beam has 3 degrees of freedom, or its kinematic indeterminacy is equal to 3. Okay. Now, so fine, kinematic indeterminacy is 3. What is kinematic indeterminacy? Number of unknown displacement quantities. Let us find those out for this. Just like we did in the truss, we should be able to write it for this one. Let's write. What are those? Note that this allows, restrains this but allows this. So this is a degree of freedom. That's my first degree of freedom. Then this is a pin roller, right? So it allows free rotation. So this is another degree of freedom. This one, this joint restrains both the motions but allows it to rotate, and that is my third degree of freedom. So in other words, this simply supported beam, if I knew the horizontal displacement of this point and the rotation at this point and the rotation at this point, I would be able to give you how this structure has displaced. So if I knew these displacement quantities, I could draw the displaced geometry of the structure. Okay? So this in essence defines the kinematic indeterminacy for beams and frames. I just want to introduce one more joint that you're all familiar with, and so I will take up another statically determinate structure. This is a cantilever beam. What is the kinematic indeterminacy of this cantilever beam? Well, let's go. How many joints? 1, 2. So 2 joints. 2. So how many unrestrained degrees of freedom? Again 6. Unrestrained degrees of freedom are 6. So now you need to find out the number of restraints. How many restraints? Well, let's look at this joint. What is this joint? This is a fixed support. What's a fixed support? A fixed support is one which restrains the point from displacing in any direction. It also restrains the rotation of that point. In other words, how will this thing displace? This will displace something like this. At this point, the slope would be 0. The displacements both vertically and horizontally would be 0. Okay? So completely restrained. Okay, what about this point? It's not restrained. It does not have any support. How many restraints? What does this restrain? It restrains vertical, horizontal, and rotation. So there are 3 restraints. So the kinematic indeterminacy, 3. What are those 3? 1, 2, 3. Simple. Okay? So for a beam, you should be able to get the kinematic indeterminacy, or the number of degrees of freedom for the structure. Okay. Now let's move on to a frame. Kinematic indeterminacy for a frame, and let me look at a simple frame. Okay. Now note, I just said that the kinematic indeterminacy for both a beam and a frame are computed in exactly the same fashion. Okay. So I can use the same algorithm that I developed for the beam. Look at this. How many nodes? 1, 2, 3, 4. So there are 4 joints in this structure. So following my procedure, each joint unrestrained has 3 degrees of freedom. So the number of unrestrained degrees of freedom is equal to 3 into 4, 12. So unrestrained degrees of freedom is 12. Now we need to find out what are the restraints in the structure. How many supports? 2 supports. What are those 2 supports? One here, one here. What are they? Fixed supports. How many restraints does a fixed support give? 3. So how many fixed supports? 2. So what are the restraints? 6. 2 into 3. 2 supports, fixed supports with 3 restraints each. So how many degrees of freedom? 6. Kinematic indeterminacy, remember, is the same as degrees of freedom, 6. What are they? Now I should be able to draw them. What are they? 1, 2, 3, 4, 5, 6. The vertical, horizontal, and the rotation of this joint. The vertical, horizontal, and rotation of this joint. 3 per node, 6 degrees of freedom. If I know these 6 displacement quantities, I can draw the displaced shape of this frame. Simple. Now, I want to bring in the concept of constraints. You see, typically what we do is, when we consider beams and frames, we tend to neglect the what? We need to stop something, right? What do we not consider in a beam or a frame generally? We tend to say that neglect the axial deformations. Why? Because by and large in a beam and a frame, the main way that the loads are transferred in a beam and a frame are through flexural deformations. In other words, the structure bends to take the loads. Okay? And when you have flexural deformations and they are very large, the axial deformations, they are there. Remember that. The axial deformations are not 0. It's just that they're very small. Okay? And we tend to say that, well, forget it. The structure is neglect the axial deformations. Okay? Now, when we neglect the axial deformations, what happens? Well, let's see. Let me go back. To my simply supported beam. I neglect the axial deformation of this member. Okay, I neglect. So therefore, what am I saying? It is axially rigid. Now note, in general, you will see, think about it, when you find out for a statically determinate beam, what are the forces that you normally find out? The shear force, bending moment. Do you ever find out the axial force? You don't. So therefore, implicitly without knowing, you are actually neglecting axial deformation. You never explicitly mention that. Okay? When you're analyzing a frame or a beam, you never explicitly state that. But you're implicitly assuming that the axial deformations are neglected. In other words, the member is actually rigid. So what happens when you have a member which is actually rigid? What happens here is now that you are constraining the structure. It has an effect. It has no effect on the degree, on the static indeterminacy of the structure. Remember that. But it has a tremendous effect on the kinematic indeterminacy or the number of degrees of freedom that you get from a structure. You are constraining a structure. So what do you do? Actually rigid. What does that mean? Let's look at this. When I say that this member is actually rigid, what am I doing? Think about it. This cannot go anywhere. This can move horizontally. Forget about the rotational degrees of freedom. I'm looking only at the axial deformation. What happens? This can go this way. So if this goes this way. What happens when this goes this way? What effectively happens to this member? This joint cannot go anywhere. This joint can move horizontally. And when it moves horizontally, what happens? The member is either actually shortened or if the displacement is this direction, it's elongated. In other words, this degree of freedom actually corresponds to the axial deformation of the body. Okay? And if this member is actually rigid, since this point is not going anywhere, can this point go anywhere? It can't. It's actually rigid. It cannot deform axially. If it cannot deform axially, this point cannot go anywhere, it means that I know this displacement. This displacement has to be 0. Okay? So therefore, do you understand what's happening? By making the structure actually rigid, what have I done? I've eliminated a degree of freedom. Now, if I say that this beam is actually rigid, how many degrees of freedom does this beam have? 1, 2, the 2 rotations. It's a 2 degree of freedom structure. Simple. Okay, but how do I put it into my algorithm? You see, I always truly believe that unless you have an algorithmic way of computing static indeterminacy and kinematic indeterminacy, you are always going to flounder, because you wouldn't know how many indeterminacies there are in the structure, both static and kinematic. So let's go back to the algorithmic way. How do I include this effect in the algorithmic way? So let's go back. What we define is 2 joints, unrestrained degrees of freedom, 2 into 3, 6, restraints, 3 minus 3, and now what have I done by making it actually rigid? Constraining the structure. So I say a new thing, constraints. Constraints also reduce the number of degrees of freedom in the structure. Okay. In this case, how many constraints? Think about it. Actually rigid, what have I done? I've made this into 0. So how many constraints do you think an actual rigidity in a member brings in? 1. Okay. Because a single degree of freedom defines the actual deformation of a body, of a member. And so when I make it actually rigid, that is the constraint that additional constraint that I am giving, that this body cannot deform axially. I am making 1 constraint per member. How many members are there in this structure? 1. So 1 minus 1. How many degrees of freedom? 2. I've already shown you the degrees of freedom in the structure. So algorithmic. So algorithm, what is the algorithm for getting the kinematic indeterminacy of a beam or a frame? Start off by finding out how many joints there are in the structure. Multiply the number of joints by 3. That gives you the total number of unrestrained degrees of freedom. Then find out the restraints. What are the restraints? The supports. The restraints are provided always by supports. So you find out, go to every support and find out what kind of restraint it gives. Add up all the restraints from all the supports. Okay, those are the total number of restraints. Those are to be subtracted from the unrestrained degrees of freedom. Now in addition to that, you need to look at the constraints. Constraints. What are the constraints? Well, member is actually rigid. If a member is actually rigid, how many degrees of freedom? Constraint? Single. Per member. Per member 1. Okay? And so you subtract the total number of constraints and you've got your degrees of freedom or the kinematic indeterminacy of the structure. Now let's go to the frame. You might say, how does this work? Let's go to the frame that we were looking at. And I say that all the members are actually rigid members. So let's now see how I compute the degrees of freedom. How many joints? 1, 2, 3, 4. How many members? 1, 2, 3. Okay. Now the unrestrained degrees of freedom. 4 joints. 3 into 4, 12. Restraints, 2 fixed supports. So restraints, 2 fixed supports is 2 into 3 restraints, 6. Constraints, How many members? 1, all actually rigid. So constraints 3. So these are minus. How many degrees of freedom does this structure have? 3. So a frame where all the members are actually rigid, okay, has 3 degrees of freedom. Now what are those 3 degrees of freedom? Let's look at it. Okay, it's very interesting. What did I have in the previous case? Let's look at the previous case and let's look at this case. And I'm going to draw all the previous case ones. When I did not have the constraint of axial rigidity, these were the 6 degrees of freedom that I had. Now let's look at what happens. 3 of those have to disappear, right? Because my kinematic indeterminacy for this structure is 3, right? So I have to make 3 displacements disappear. How do I make? Remember, it's not 3 displacements that I'm making them disappear or I'm making them equal to 0. It may so happen that 2 displacements are equal to each other, in which case it is only 1 degree of freedom. Because remember, the kinematic indeterminacy is the minimum number of independent displacement quantities that I need to define to be able to give the displaced geometry. Now if 1 degree of freedom is equal to another degree of freedom, then what happens? I need only one of them, right? Okay, so therefore let's look at this. Now let's look at this degree of freedom. What does this entail? This joint is not going anywhere vertically. If this joint moves vertically, what happens? That means this member is being actually deformed, but it's actually rigid. So therefore what happens? I know that this displacement is equal to 0. Similarly, I know that this displacement is equal to 0 because this displacement would entail this column deforming. What else do I know? Think about it. This member cannot actually deform. What does that mean? Think of this degree and this degree of freedom. What if this joint displaces by 1? How much will this joint displace by horizontally? Since this member is actually rigid, if this displaces horizontally by 1, so will this. What does that mean? That means that these 2 displacement quantities are the same. They're going to have equal value. So I need to only consider one of them. So remember, I'm not saying that this is equal to 0. No, it's not equal to 0. However, I'm eliminating this degree of freedom because this and this are the same. You could do either one of them. Either this or this you could eliminate. So then, what are my independent degrees of freedom for this axially rigid frame? 1 rotation, 2 rotation, 3 horizontal displacement. Those are my 3 degrees of freedom for this axially rigid frame. So you see, it's fairly simple. There is no problem now you should have in computing the kinematic indeterminacy of a planar structure, be it a truss, a beam, or a frame. How do you go? Find out the number of degrees of freedom per joint depending on whether you have a truss structure or a beam structure. If it's a truss structure, number of degrees of freedom per joint is 2. Find out the number of joints, multiply by 2, then find out the restraints, and you've got it. Remember that you cannot, an axial member cannot be constrained, okay? Because if you stop the axial deformation of a truss member, what else is left? Nothing. It cannot deform at all. Okay? So typically in a truss structure, you never have constraints. You only have restraints provided by the supports. When you come to a beam and a frame, if you do not stop any of the deformations, then you have 3 degrees of freedom per joint. Number of joints gives you the total unconstrained degrees of freedom. You find out the restraints, subtract them. Furthermore, if you want to stop the deformation, you want to neglect the deformation, not stop, you want to neglect the deformation of a particular member, then you have to consider that member as a constraint. So if you stop the actual deformation, for each member you neglect the axial deformation, you have one constraint, and you find out if you make all of them, then you have that many number of constraints. Okay. So this is relatively simple. I hope that at the end of this treatise, you should be able to find out the kinematic indeterminacy and static indeterminacy of frames. I am now going to show one more constraint, because you might have a constraint like this. Think about it. And this beam is totally rigid. In other words, this beam cannot deform axially or flexurally. What happens in such a situation? You see, axial constraint, I have already shown it's 1. 1 for axial. How many for flexural constraint? Because you are making it flexually rigid also now. How many constraints? Let's look back at this simple beam. How many degrees of freedom does this beam have? It's actually rigid, right? So how many degrees of freedom? 1, 2. Now let me make this beam totally flexually rigid. It can't bend. If it can't bend, what happens? This is 0, this is 0. So, if you have flexural rigidity, how many constraints per member? 2. So therefore, let me look at this. How many degrees of freedom? Remember that when this was not flexurally rigid, we had 3 degrees of freedom. So I'm going to start from there. 3 degrees of freedom. How many constraints? Additional constraints? Additional constraints due to flexural rigidity, 2. How many degrees of freedom? 1. What is that? This one. Okay, so that's all. That's all I have to say. Now I want to show you some structures, and we will go through and compute how you are going to compute the kinematic and static indeterminacy of these frames. So let's look at the first frame. What is this? This is a propped cantilever. Okay, it's a statically determinate structure. Why? Because if you look at it, how many support reactions? 4. And how many equations of equilibrium? 3. So it's a statically indeterminate structure. Now let me have a look at another one. Here what you have is, you have this joint. You have the left joint, which you have allowed it to move horizontally. You allowed it to move horizontally. If you allow it to move horizontally, look at what happens. Suppose I apply a horizontal load to this beam. What's going to happen? Think about it. This beam is going to move because there is no horizontal restraint. It only has 2 vertical restraints and a moment restraint at the left end. This structure is unstable. Okay. So therefore, understand one thing, that it's very important before you start looking at static indeterminacy, you need to know whether it is unstable or stable, and you can only find out the indeterminacy of stable structures. Look at this. This is stable. It's a cantilever. Okay. Now let us look at certain point. Let's look at this particular member. Look at the top. How many degrees of freedom do you think it has? Well, think about it. There's one frame, one member. How many joints? 2 joints. Okay. There are 2 joints here, 1 here, 1 here. So 2 joints. How many degrees of freedom? So unconstrained, 2 joints, you have 2 into 3. How much is that? 6. So you have unconstrained degrees of freedom is 6. Now let's look at the restraints. Restraint, this joint is fixed. Fixed, how many constraints? Restraints? 3. What about this restraint? 1. So how many restraints total? 4. 4, so that means unconstrained 6 minus 4, 2 degrees of freedom for this structure. What are the 2 degrees of freedom? One is this and one is this rotation. So this displacement and this rotation. Now in addition to that, I'm going to say that this is actually rigid. This is implicit. I don't even have to state it. Typically for a beam, unless you explicitly allow axial deformation, you assume it to be actually rigid. So if it's actually rigid, constraint 1. How many degrees of freedom? 1. Which is that? This rotation. So kinematic indeterminacy 1. Static indeterminacy, how do I go about it? Well, 3 plus 1, 4. 4. So how many equations of equilibrium? 3. Okay, so what is the static indeterminacy? 1. So this structure has a single kinematic indeterminacy and a single static indeterminacy. Let's look at a few other structures. Let me look at this structure. What is this? This is a multi-span beam. In a multi-span beam, this is the structure. I need to find out its number of degrees of freedom and the static indeterminacy. Simple static indeterminacy, if I remove this, it becomes statically determinate. So there is only one static indeterminacy. Kinematic, how many? Let's go through it. 1, 2, 3. 3 into 3. 3 into 3. 9. How many restraints? 1, 2, 3, 4. Restraints total 4. Then 9 minus 4, 5. Static indeterminacy is 1 and kinematic indeterminacy is 5. Let's quickly look at another structure. This structure. How many redundant forces? Well, I'm not going to go into this. 1, if I release this and I release this totally, I get a simply supported beam. So it has 4 redundant forces. So static indeterminacy is 4. Kinematic, 3 joints, 1, 2, 3. 3 into 3, 9. Restraints, 3 here, 1 here. So 2 degrees of freedom, and you are shown the 2 degrees of freedom. You have a truss. For a truss, what is the static redundancy? Remember that each one is triangulated, so it's internally determinate. And if I remove one of these, so if I remove this, it becomes externally determinate also. So this is the only redundant force. So the static indeterminacy is 1. And the kinematic, you have 1, 2, 3, 4, 5, 6. 6 into 2, 12. 12 minus 4 restraints, 2, 1, 1. 4 restraints gives you kinematic indeterminacy 8. Look at a frame structure. We've already seen this. It's 3 and 6. Static indeterminacy 3, kinematic indeterminacy 6. And that brings us to the end of this lecture. So therefore, at the end of this lecture, I am going to assume from here on out that given any structure, you should be able to find out its static indeterminacy and kinematic indeterminacy, or kinematic indeterminacy I replace sometimes by degrees of freedom. Okay? Thank you. So we will continue next time by looking at some methods from which we can use to do our structural analysis.